last time we were talking about the kind of generalization of face-based representations, and when we first introduced this, I hinted at the fact that there's not necessarily a unique way to define a face-based representation, and it depends on what you're trying to. There's different representations that have different physical interpretations and different uses. And they all arise from the fact that the X and P don't commute, or equivalently A and A dagger don't commute. And so it's not obvious how to take an operator that's some function of X and P or function of A and A dagger and turn it into a function on face space. And one way to think about that is to say, I can order this in a power series that's what's called an operator ordered series. So, or S ordered, as it's sometimes called. And I can write it where I write all this A daggers on the left and A's on the right. That's the normally ordered series, or I can symmetrically order them in terms of all possible permutations of A and A dagger, or put all the A daggers on the right and the A's on the left. That's called anti-normally ordered. These operators are all the same operator, they're equal. So these coefficients, which I'm calling C, where S can be +1, 0, or -1 for normally ordered, symmetrically ordered, or anti-normally ordered. These coefficients, C, S, are different coefficients, okay? And the S-ordered face-based representation of the operator is what I get by substituting A dagger for A with A star and A with alpha. A dagger with alpha star, A with alpha, with these different coefficients. So this will be a different function for different operator orderings, okay? And it's what I'm calling the S-ordered face-based representation. Now again, I warn you that in the literature, everyone has this as -S, but this is the right order because this is the S-ordered representation. Now there's a reason why people have the other idea, and that's because the way you obtain this S-ordered representation is by tracing it with the -S ordered delta function with this pi normalization. So some people would, which is everybody else other than me, would call this the -S representation. But that's just completely confused because this is the S-ordered representation anyway. Okay, so we obtain this by looking at the trace of the operator with the -S ordered delta function with this pi. Okay, so these are the different S-ordered delta function. This is the normally ordered delta function. This is the symmetrically ordered delta function, the one we've talked about for some weeks, and this is the anti-normally ordered delta function, which happens to be the projector onto the coherent state. Okay. Now, just to show that we could look at that this works for all the different orderings, I thought I just had this in my head, but I didn't. So I just wanted to the details of this algebra are not important, but I'll just show you that it works. So if I wanted to find the anti-normally ordered representation, I have to trace that with the normally ordered delta function, okay? Which, by the cyclic property of trace, I can move to the other side, okay? And now I'm plugging in the anti-normally ordered series into that thing, okay? So now I have all the A's on the left and all the A daggers on the right, and now I can shove in the resolution of identity, which is where I really wanted to do it, in between those guys. And when you do that and you take care of all the delta functions, indeed, you get that this is the right power series. So tracing the operator with the normally ordered delta function gives you the anti-normally ordered representation, as expected. Okay? Phew. Okay. Right. So, there's, all these things. There's this kind of duality, thus, that we have between these things. So what we have is that a resolution of the identity can be expressed in terms of the this duality relation. Okay, so these the S-ordered delta function is orthogonal to the minus S-ordered delta function. Okay. And so thus I can look at, for example, some observable, which if I write in the superoperator notation, gives me the S-ordered representation. So that tells me that an operator is a superposition of the S-ordered delta function with the S-ordered. I keep track of all these minus signs. They're all over the place. Okay. So this just says I've given the S-ordered representation. And then, moreover, if I wanted to look at the trace inner product between two operators, right, that's equal to the trace of A dagger with B, then that's equal to, by this rule over here, A ds alpha B T minus S alpha, that's B S alpha, and this is A S star of minus S. So that's one way of expressing this inner product between two operators in terms of their respective phase space representations. And importantly, we have this kind of duality between the two different orders, plus with minus. The symmetric is the same in both cases. Importantly, if I'm asking about the expectation value of some operator, that is the trace of rho with A, where rho is the state, which is can be thought of in this notation like that. Rho is a Hermitian operator, so I can do that, which is equal to, by this definition, or equivalently, could do it the other way around. And this is what we're calling the S-ordered quasi-probability. So, the Wigner function is the S equals 0 order. That's W of alpha is this guy. The Glauber Sudarshan representation is S equals -1. That is the anti-normal order. P of alpha is the anti-normal ordered representation. And the Husimi representation is the S equals 1 is the normally ordered rep of rho. And we call that the Q function. Plus 1. Okay, so these are three well-known representations. They are related to different operator orderings, and they have different utility, which we'll emphasize today again. Okay, as we said, the way I get the normally orders I have to trace with the anti-normally ordered delta function, right? So this is equal to 1 over pi times the trace of rho with t plus 1, minus 1, which is the trace of rho with the projector on the coherent state. So the Q function is the probability, is a true probability density. It's always positive. The Q function is the trace of rho with the POVM element. Where the POVM element is this. And that POVM element is related to what we have as a heterodyne measurement. A simultaneous measurement of X and P. And it's a true probability density where these are the different measurement outcomes corresponding to these POVM elements. They're continuous variables, so it's a probability density, but it's an honest-to-God probability density. Using this relationship over here, what we see is that rho is equal to the integral over alpha p, the p function, times the anti-normally ordered which is what we said our definition of the P function was, as a statistical mixture of coherent states. Very good. Any questions about any of that so far? So we were talking about last time the question of existence. Now that's a tough question to get into, but you know, we do what we can. So just because I wrote down a power series doesn't mean that this converges. So we have to think about that a little bit. And to do that, the best way to do it is to think about the characteristic function. You remember the characteristic function is the Fourier transform of the quasi-probability. So for the Wigner function, we define this guy is the Fourier transform of the Wigner function in the 2D phase space, which is equal to 1 over pi, the trace of rho with the displacement operator. So this is the case, I can call this for the symmetric order, s equals 0, right? Generally speaking, I'll define the SR, now I have to trace with minus s. So that's the S-ordered characteristic function, which is the Fourier transform of the S-ordered quasi-probability. So, and that could be the Fourier transform of the P function, the Fourier transform of the Wigner function, or the Fourier transform of the Husimi distribution. So D sub S is the following. So D is defined as this. That's D0. That's a symmetrically ordered case. That's our friend, the displacement operator. It's the only friend we have. I know it's a tough life. Right? So that's symmetrically ordered, and that's how we defined it, or that's sort of how we defined the symmetric delta function in the first place. D equals plus 1 means this, whose Fourier transform is this. Okay? D equals minus 1 is this, whose Fourier transform is this. Okay? And using Baker-Campbell-Hausdorff, what we have is that the S-ordered displacement operator can be obtained by a Gaussian weight-like thing, or something that's quadratic in beta, multiplying the displacement operator. You can play around by yourself to show that that's true, right? Just using, so that tells us something about this characteristic function and its different properties depending upon whether S is plus 1, minus 1, or 0, okay? So for that, I want to just do a little aside. Square normalizable functions and Fourier transform. So let's say I have a function on the phase space, provided as a function of alpha and alpha star, or vice versa. Then I'm going to find the norm squared of this as the integral of this function over the whole phase space. Okay. If this is finite, we say it's square normalizable. Okay. It's in the group we might call L2 on the phase plane. They're L2 square normalizable functions, right? Now, if the Fourier transform of this is defined as we have done so on the phase space, then by Parsifal's theorem, it's easy to show that this is equal to this. I mean, you just plug that in and there's some delta functions that happen, and I could say that if one is finite the other. So the question is, this thing exists is sufficient to say that in the inverse Fourier transform, so this thing exists, it's sufficient for the Fourier transform to be square normalizable. If my Fourier transform is square normalizable, if this function, f tilde, is square normalizable, then that is sufficient to say that this thing exists. I'm not sure that's a necessary condition. We had this discussion a year ago. Someone who's smarter than me can understand that, but for now, this is sufficient. Okay? So the question is the characteristic function a square normalizable function or not? If it is, then the corresponding inverse Fourier transform, which is, say, the Wigner function or the P function or the Q function, is guaranteed to exist. Okay? Now, I can relate that to something about what we call operator norm. I'm going to define a bounded operator to be one such that it's is finite. That's the Hilbert-Schmidt norm. Okay. So if this is finite, then we'll call it a bounded operator. In an infinite dimensional Hilbert space, we're not guaranteed for every operator to have a finite bound. Not all operators are bounded. But from what we just described over here, the trace inner product is related to the product of those two functions, right? So this trace inner product can be expressed as and for s equals 0, it's the square of that, right? Which is also the square of its Fourier transform by Parsifal's theorem. So a bounded operator is one for which these functions are square normalizable. So if it's a bounded operator, those things are square normalizable, or at least this function is square normalizable. Let's look at the density operator. Is the density operator a bounded operator? Let's look at rho. Well, that's the trace of rho squared, because rho is Hermitian. Is that finite? Yes, it is. It's always less than or equal to 1. Which means that the characteristic function of the Wigner function is finite. Which means that the Wigner function always exists. For any state. So, existence of Wigner. That's always a good. What about the Husimi representation? Well, there's a couple of things we could say about the Husimi representation. If I look at the characteristic function of the Husimi representation, right, that's the Fourier transform of the Q function. Well, what we said over there somewhere, because of that effect, what I see is that that's s equals plus 1. So that's, I have to trace this rho with d minus 1. But that's equal to e to the minus beta squared over 2 times the characteristic function of the Wigner function, because Deutsch is crazy and you have a plus 1 here and a minus 1 there. So, just from this fact, if this thing is square normalizable, this is even more square normalizable. It's going to be easily square normalizable because you're going to be damping out those very high. So this is for sure square normalizable. Even more so.
It's a mathematical term.
Whatever that means. You can decide. And that was clear because the Q function is this, and that clearly always exists. Right? No matter what rho is. So that's all self-consistent with all these Fourier transform hoo-ha. Right? What about the P function? The P function is the anti-normally ordered representation of rho. And the characteristic function of Glauber, Sudarshan, is e to the plus beta squared over 2 times that. Is that going to be square normalizable? What's the answer? It depends, right? It depends on how fast this thing falls off with beta. So that means this is square normalizable only if the characteristic function of the Wigner function falls off at least like a Gaussian.
Has to in every direction.
Yeah. You know, right? Now, if this is equal to e to the minus beta squared over 2, well, from a physicist's point of view, that's good enough, right? Because then the characteristic function would be flat. It's not really normalizable. But if you take the inverse Fourier transform of something which is flat, you get a delta function, okay? So, and we know that we'll come back to that, that's the case of a coherent state. But really, that's the borderline. Any other pure state is not going to have a p function. So the p function rarely exists for pure states. Yes?
Does it ever exist except for coherent states? For pure
No.
states? Okay, so that's it.
To my knowledge.
Yeah. Okay. I mean, it seems like it should be just that.
I think that's it.
Okay.
I think you're right. I haven't thought about it carefully, but I think the answer is yes. Good. So, now these relationships here tell us relationships between the different quasi-probability distributions. So, for example, the Q function is the Fourier transform of the characteristic function, or the inverse Fourier transform. And using what we wrote up here, that's equal to e to the minus beta squared over 2 chi 0 e to the alpha beta star minus alpha star beta. Right? So now I ask you just intuitively, because everyone here is very intuitive, what is the inverse Fourier transform of the product of two functions? It's a convolution, right? Everybody's doing it. Okay, so come on, baby, do the convolution. That's how I always remember it. My life's a musical. So, the inverse Fourier transform of a Gaussian is a Gaussian with the opposite. You know, there's a factor of 2 because you go, so it's e to the minus 2 beta minus alpha squared. So what we see is that the Q function is a kind of coarse-grained version of the Wigner function. You're taking at every point and you're smearing it out by a point spread function, which is a Gaussian. So the Q function is a coarse-grained version of the Wigner function. And the Wigner function is a coarse-grained version of the P function. There's too many dummy variables here. This is alpha prime. Now it makes sense.
The integral is over.
The integral is over alpha prime. Now it completely makes sense. And the Q function is a doubly, even super smeared with a fatter Gaussian on the P function. So there's this kind of coarse graining that kind of means something. Think about that a little bit in a moment. let's just think about some examples, okay? Make sure I haven't forgotten something I wanted to say. So far, so good. So, let's look at some examples. Coherent state. We can do this by eye, because we know that the coherence, that the row is that. So we can just read off what's the P function. If the answer is going to be, this is going to be equal to, what's the P function of a coherent state? A delta function. I mean, we could do the formal thing, that's what we just said, where it's just, I'd find that the characteristic function was flat and blah, blah, blah. What's the Wigner function? Well, I can do the convolution or anything I wanted. If I do the convolution over here, then this is equal to 2 pi even minus 2 alpha minus alpha naught squared, which we got in a previous lecture by finding the characteristic function, which is a Gaussian, and then taking the inverse Fourier transform. And what's the Q function? It's also Gaussian, but it's fatter. But maybe before I write that down, let me just remind you that this is if I go to the quadratures, this is 1 over the square root, 1 over pi e to the x minus x naught squared, e to the minus p naught squared. And the Q function is that. That's twice the variance. Okay? Let's continue. What about a squeeze state? Let's talk about a squeeze vacuum. What's the P function? Do you think it exists? What's your guess?
It falls off wrong.
It's just totally, we know that there's no pure state. We just said there's just no way. So this is singular, more than a delta function. delta function is kind of on the edge of singularity that we can deal with. You know, it's just, if it's flat, then we call it delta function, but if it blows up, then, yeah, right? So there is no P representation. What about the Wigner function? What's the Wigner function of the squeezed vacuum? It's a Gaussian, right? With different, so we could write this as in the quadratures as pi 2 pi sigma x squared e to the minus x minus, well, let's say it's squeezed vacuum. X squared over 2 sigma x squared 1 over square root of 2 pi sigma p squared e to the minus p squared over 2 sigma p squared. The sigma x squared is e to the minus r times a half. And sigma p squared is e to the plus r times a half.
So for your P, doesn't it depend on the amount of squeezing?
No matter how much squeezing.
Really?
No matter the tiniest amount of squeezing, and it blows up.
Asymptotically to non-squeezing.
Yeah, the problem is that a delta function is already
Oh,
singular, so
okay.
it's not really, there's no analyticity. It's all singular, even for the coherent state. But we call that a delta function because we're physicists, right? This is positive everywhere, the W. What about the Q function? Well, the Q function is going to be the same thing, but sigma x squared will go to it'll be chubbier. It'll have a bigger variance. Come back to that in just a moment to understand what that means physically. What about a Fock state? What about the P function?
Derivatives of delta functions.
Yeah, they're derivatives of delta functions. Yeah, that doesn't count either. I mean, there's derivatives of delta functions.
Well,
in
this
the
is
same-
that this is an infinite series.
Yeah.
Whereas this is just 1, 2,
Yeah,
3,
yeah, yeah.
5.
So derivatives of delta functions, I'll give you that.
So we can deal with derivatives with the theory of tempered
We could.
distributions. We can't deal.
We can't deal with that. But it doesn't exist by any reasonable
standard.
Yeah. What about the Wigner function? Well, we solved this earlier. It's equal to 2 over pi minus 1, except, of course, for n equals 0. N equals 0 is the vacuum, that's okay. Times a Laguerre polynomial. This exists, but it's negative in some regions. The Laguerre polynomials and all these things can be negative. What about the Q function?
Power times this function.
How would you calculate it?
Well, it's
Well, this one's easy, right? Because this, by definition, is that, which is equal to that. But how do you calculate that?
stand out.
Use the expansion of the channel.
we know how a coherent state is a superposition of Fock states. It's a Poisson distribution, right? So that's equal to 1 over pi alpha squared to the n over n factorial e to the minus. Well, I think I forgot that part here. That's also bad. Is it working? Right? This thing is everywhere positive. What do these things look like? Let's just, I want to just remind you. Right. So these were Wigner functions. And as we said, the Q function's a kind of coarse-grained or smeared out version of the Wigner function. This is the n equals 1 Fock state. As we discussed, and I remind you again, it's not so surprising if we didn't know anything about all this symmetric delta functions, or what if we had to sketch this, we're on a desert island and we're just forced to do it, because we know what the marginals have to be, and we also know that this thing, the Fock state is rotationally symmetric in phase space, right? And so it's going to have this kind of form, but it has this negative thing in it, so it has the right marginals. What would the Husimi distribution look like for this? It's kind of hidden behind this board now, but what do you expect it to look like? Yeah, I mean, you expect it, so let's just draw a picture over here. Here's phase space. Classically, if I have something which has a definite energy of the harmonic oscillator, I have a harmonic oscillator that has a definite energy, we know that the trajectory is a circle in phase space. The energy eigenstates are the eigenstates of the harmonic oscillator that have this. So we expect that the state, the quantum state of the system, is somehow in quasi-probability land concentrated around here. When we're writing it in phase space, we're not writing the energy eigenstates, we're writing some phase space representation of it. But basically the point is that for the Wigner function, it's concentrated over here with a negative part in the middle. Whereas the Husimi distribution is just going to be something that is basically concentrated around here, but with a kind of wider width. It'll be a ring. And that's a general feature. If you calculate the Husimi representation of a state, just think about wave mechanics. In this case, then what it will be is it'll be concentrated along the classical trajectories that are associated with that state. You can intuit what it's going to be in that way. And often we plot the Husimi distribution to get a sense of where the wave function is concentrated. It's in phase space. It's a much easier thing to calculate than the Wigner function, where you have to go through, you know, the characteristic function or some convolution or something or other. Okay. What about the cat state? This is the so-called cat state that we had. The cat state was a state which we said, for example, was some superposition with some normalization, e.g. Okay, that's an example of a cat state. And this is the Wigner function that we discussed, which has the alive and dead probabilities and the whiskers of the kitten or cat in between, which are the quantum interference. There's not going to be a P representation for that, clearly. It's going to be horrible. What about the Husimi representation, or the Q function?
I would guess the whiskers now turn into zeros.
Exactly, it's important. So basically, firstly, the two coherent states are going to get a little chubbier. But when we coarse grain this, there's going to be zeros. Now that's something interesting, and I hadn't actually appreciated or learned about until a few years ago, that the zeros of the Q function, through the theory of analytic functions on complex plane, completely define the state. It's what's known as the stellar representation, for reasons I don't remember. Which are the zeros of the Husimi representation. That completely determines the function state, actually. And it's a kind of an interesting representation I think is underappreciated, certainly by me, and it might be something worth thinking about in some context, because somehow how complex the state is really related to have the zeros in that. You see there will have to be zeros, because when we coarse grain this over from pluses to minus, there's going to be zeros in the state. Very good. Let's continue. Now, we have all this mathematics and this representation. Let's talk about, the utility of these different representations and what they're telling us about the state and what we would want to use it for. So one thing is calculating S-ordered correlation functions. Suppose I wanted to find the expectation value of some A dagger to the N in the M with some S ordering. Well, according to what we just said, I can look at the S-ordered representation of this averaged over the minus S-ordered quasi-probability. So for example, if I look at the normally ordered guy, that's equal to the anti-normally ordered version of this, which is the P function, which is what we studied last semester. This is Glauber photon counting theory. the anti-normally ordered guy I get with the Q function. Meh. What do we ever use that for? We don't. The Q function really doesn't give a, there's no way to measure that. But what the Q function does tell us is heterodyne. So the Q function tells us what those probability distributions, but those probability distributions are necessarily noisier because we're paying a price for measuring X and P at the same time. The marginals in X and the marginals in P are extra noisy. That's what these extra noise terms that you get in terms of your fluctuations, because you're trying to measure X and P at the same time, and you gotta pay the piper to do that. Yeah?
So yeah, obviously I don't usually care about an anti-normally ordered anything, but if I wanted to use the Q function, if that's all I had, I could take any operator I do care about and write it in anti-normal order, right? Like,
If I could do that,
if I could
except that the anti-normally ordered representation of the operator may not exist and probably doesn't. That is really, so the Q function, there's some, somewhere this, you can't really get classical theory out of that. Because whereas the Q function will exist, the operator you're trying to look at, which is in anti-normally ordered, won't exist. Because they come in these pairs. If you're looking at the normally ordered row, you gotta look at the anti-normally ordered observable, and meh. And for symmetrically ordered guy, you have these moments. Which are homodyne measurements. So what we were saying earlier about the existence of these different things, if the P function is positive, well, I want to hold off on what I want to say. What this tells us is that there are kind of different, there's a kind of hierarchy of levels of classicalness and non-classicalness in the state. If the P function is positive, measurement of any observable has a classical statistical prediction. Because all of these things are always well defined. If the P function is positive, the Wigner function is going to be positive, the Q function is positive. Anything you measure can be thought about as a classical statistical theory. And as we know, when the P function is positive, what that's equivalent to say is that the state is a statistical mixture of coherent states. And we can treat the field completely classically, and any randomness we see, we can attribute to the photoabsorption process being random, but we don't have a quantum field. And anything else we measure, like homodyne or heterodyne, also has a classical theory. If the P doesn't exist, but the Wigner function is positive, then what we would say is that photon counting can be non-classical. E.g., sub-Poissonian statistics. We can have a situation where we have squeezed vacuum, where we see noise below what would be possible just thinking about random Poisson process. But the homodyne, which we would call Gaussian measurements, because all the the x and p measurements are Gaussian functions of x and p. This is classical. If the Wigner function is negative, then this is the gold standard. Then there are lots of things where we can't have. This in between is, from the point of view of what we know about thinking about qubits, this is like the Clifford hierarchy. We can think about these things as, in the qubit world, for those, this is a little aside for those who know this, we have local gates, we have Clifford gates, and non-Clifford. Or magic. The non-Gaussian states are like magic states. If I wanted to do quantum computing with continuous variables, with x and p, rather than with zeros and ones, in principle I can do it, but I can't just use squeezing. I got to go beyond squeezing. Interestingly, well, I'd say that thought is the one that'll be the good segue we're going to talk about next.
What do you mean by local gates?
What I mean is just gates that aren't qubits. I don't have CNOT.
I mean, like, T gates are non-Clifford, but they're local in that sense? Do you mean, like, that's not supposed to be polys, right?
That would be fine if I had T gates but no CNOTs. That's completely classical.
Okay.
Yep. If I don't have any entanglement, if I only have local, I can have T gates.
Okay.
I want to talk about the problem of boson sampling. This was the first problem that was discussed as a way of achieving so-called quantum supremacy. We don't use those words anymore, but it means something. The problem is the following. So one version of it, I have some set of multiple modes. Okay? And I'm going to have some unitary that acts on those modes. And then I'm going to have the modes come out, and I do some measurement. The question is whether the statistics can be efficiently, classically simulated. Means it doesn't grow exponentially with the number of modes. If I can, a way of saying this simply is, can I draw on a random number generator that I generate on a class computer, can I draw those random numbers from the statistical output that the quantum system gives? If I can't, then I would say that's a problem that's creating a probability distribution that I can't create classically. That's a way of saying, a first way of saying I might have something that quantum mechanics can do that a classical Turing machine can't. So the first problem that was looked at by Scott Aronson and a student, I don't know his first name, but his last name is Arkhipov, was to look at the question where U is linear optical network. Meaning, this is just beam splitters and phase shifters and lenses. It's a big interferometer, okay? Now, as we discussed, linear optics seems like, that's not going to do anything, because in particular, what we know is that if we put in a coherent state into each of these modes and have a linear optical network, what comes out? So this is a product state. This is what's the output state that comes out of this interferometer? It's a product state of coherent states, right? So I'm going to get where each one of these things, alpha sub I, is just some matrix on the input modes, right? Related to the interferometer. So that seems like it's not worth anything. But it turns out that if instead I put in not coherent states, but I put in states that are Fock states. Well, actually, let's put in single photon states. I put one photon in each of these modes. have to be identical. So if I put a wave packet, I've got to have the same single photon wave packet entering everything, so I can't distinguish them. But there's exactly one photon in each mode.
They're coherent.
What's that?
If they're coherent, you send them to coherent.
Well, no, it's not a coherent state. I have a single photon, but I could have a single photon wave packet. A single photon does not have to have a definite frequency. I can have one photon in a pulse. Okay? We'll talk a little bit more about that next week. So now what I'm going to do is I'm going to have photon counters that are going to count the number of photons in each mode. And I'm interested in this probability distribution. The total number of photons is n, but they can be redistributed in any way I like. And I want to calculate this. What is that going to be? It's complicated is the answer. It depends on the permanence of this matrix. The permanents are the determinants, but with positive signs rather than negative signs. It turns out that calculating the permanence is a very hard thing to do. It turns out that this is not simulable. That's the problem of boson sampling. Now, but we had linear optics. But the point was the initial state was not a coherent state. So the whole transformation is something which may not have a classical distribution. Now I have the final question for you. Suppose now, instead, I'm going to put in squeeze vacuum or squeeze coherent state, if you like, into each mode. What comes, and now I have a linear optical network. The question, this thing has a positive Wigner function. Has negative, it has non-existent P representation. But now I ask you, after I go through this linear optical network, well, there's a few things we'll learn. Firstly, the output state will be an entangled state. It will not be a product state of the modes anymore. In the same way that for the qubit world, Clifford gates create entanglement. The linear optical network takes a Gaussian state and preserves the Gaussianity. This will be a Hogarth problem. Sorry. So linear optic networks will take a squeezed set of squeeze states to an entangled set of squeeze states. So is this enough of a resource to generate quantum supremacy? Doesn't seem like it, because it's kind of a positive Wigner function to a positive Wigner function. That doesn't seem good. But what if instead of if I did homodyne measurement, that's like measuring in the measuring in the computational basis of the X and P. That will be completely sampleable from a Gaussian. But instead, suppose I count photons. That's a non-Gaussian measurement. Will this probability distribution be simulable or not, or some version of it? That's an interesting question, and it's very recent work. that's been done, particularly in China, on what's known as Gaussian boson sampling, where you can have some arguments based on not the permanent, but the so-called half-mean or something like that, I forget, that shows that in certain circumstances, this also can show quantum superposition. Even though you're starting with a positive Wigner function, if you're not doing a homodyne measurement, but doing photon counting, the photon statistics can be something which cannot be describable by a classical statistical theory and would require something more. So this is where these, the research, these different levels of classicalness tell us something about the complexity in the system and the degree to which there exists a classical description of it, which could be a resource for some information processing tasks that we could not do efficiently classically. So that's one of the stories of QP and W. Phew, we're done with that. But our next story is this whole story of entanglement. The story, there's some intimate relationship here between these different kinds of classicalness and notions of, when we get entanglement, which is another way of saying something is non-classical. And that's what we're going to talk about for the next few weeks before spring break.